My name is Nima Naderloui, and today I will present our paper Rectifying Unlearning Efficacy and Privacy Evaluation, a new inference attack perspective. This work is a collaboration with colleagues from UConn, Illinois Tech, Stevens Institute of Technology, and Alibaba Group, where our motivation is simple. Unlearning has become increasingly trending to preserve privacy, but evaluation remains surprisingly tricky. Over the last few years, we have seen an explosion of unlearning algorithms, mostly inexact unlearning algorithms, and papers that are showing incremental improvements. These incremental improvements leading the sense to suggest that unlearning is already a solved problem, at least for vision models. But we argue the apparent success might not came from the method themselves, but from the limitation in current evaluation frameworks. So the question is, did unlearning really succeed in 2025? Existing evaluations mostly rely on membership inference attacks. And membership inference attack for unlearning is an attack to distinguish if a sample is unlearned or not. It's a measure by attack accuracy and strict metrics like TPR at low FPR. Here is an example of two recent results showing that unlearned models only differ from retrained models by less than 3% in MI accuracy on the left figure, on the left table. These metrics mostly rely on aggregated metrics such as accuracy gaps or report only subtle differences. State-of-the-art privacy attack on the right side is showing that some inexact unlearning algorithms actually exist, that they can achieve MI accuracy below 10%. For example, algorithms like Scrub and sparsity can achieve this performance. In general, we identified three key limitations in current evaluation. Most works consider average case MIs, such as population MIs or MIs using test data as benchmarks, which are inherently weaker. Many works run MIs on small fractions of the randomly selected data as forget data, while in worst case, an adversary might be interested in more highly memorized or high-risk samples. And comparisons with retrained models are incomplete because two models might have very similar overall accuracy, but behave very differently on specific samples. We will discuss these limitations through this presentation. Let's step back and see the training and unlearning framework. Users are sharing their data, and a model is trained. Then privacy regulations like GDPR and CCPA allow them to request removal of their data for any reasons. In practice, these requests typically form only a small fraction of training data. For example, it can be less than 1% up to 10%. And as retraining from scratch for such requests is not feasible, service providers thereby rely on efficient inexact unlearning algorithms and release unlearned models, claiming to adhere to the right to be forgotten. So GDPR and CCPA are preserving privacy for users by data removal. The gold standard is still retraining from scratch without the removed data. This serves as a reference for both efficacy and privacy. So unlearning should be as close as possible to retraining, ensuring effective data removal, while preserving leakage about unlearned samples in final releases of the model. These two criteria form the foundation of our evaluation framework. So to capture these requirements, we frame the evaluation through the lens of the membership inference attack. As we said, membership inference attacks are basically aimed to distinguish two cases, being member or non-member, based on the signals that we can get from the models by probing the model and get the loss confidence or logits. And here we define 4 distributions because we have 2 models. One of them is trained models and the other one is unlearned models. In, out, unlearned, and held out. In are the models that train with a given sample. and out is the models that are trained without that sample. Unlearn all the distribution of the models after unlearning the specific sample. And held out are distribution of unlearned models when the sample was never part of the training. So informally speaking, if unlearned distribution is close to held out, the privacy is preserved, and we achieve privacy preserving. And if unlearned is close to out, we can call this unlearning effective. And the closer, the better the effectiveness. Now let's begin with privacy leakage. At first, this seems very straightforward because we just need to query the unlearned model and test whether the sample was unlearned or never part of the training by comparing unlearned and held out distribution. But here is a challenge or trick that memorization, we know that is not uniform. And here, for example, some samples like Jamie are far more vulnerable. Many other samples are better generalized, so they are well protected, and their presence in the training set hardly change the model's behavior. Many works consider random sample unlearning for evaluating privacy leakage. Actually, this gives credit for protecting samples that were already safe to the unlearning. For example, the sample here, Alex, if considered for evaluation for unlearning privacy leakage, will give extra credit for unlearning protection while Alex was already protected by itself. So we argue evaluation should focus on high-risk samples, and later we show how injecting vulnerable samples as canaries into forgetting requests highlights these kind of risks. Following the same principle as privacy auditing. From a game theoretic perspective, you might see this as a targeted attacks, where adversary choose some samples that he's interested on, and the challenger will randomly select if the sample is going to be unlearned or the sample would be out of the training. Now let's consider efficacy. So one might try to measure efficacy by repeating the same process as privacy leakage, that it queries the unlearned model and tests whether it looks like training. But this fails in practice because of the output suppression. So unlearned models' outputs are suppressed, and querying the unlearned models gives weak membership signal because we want to compare the unlearned sample model with retrained model. So if we call a suppressed model, we usually get weak signalings. So we need to find a way to calibrate this suppression. Here is a closer look on what happens. We show the mean and variance of the shadow models on the logit scale confidences of 4 distributions, and we use scrub unlearning, and this is on cipher 10. This is mean and variance of the Gaussian distribution of the shadow models. When querying unlearned models, most points fall into suppressed regions. That is the region that is shared with the blue and red dots, and making efficacy very indistinguishable. We therefore need a way to calibrate suppression, as we said. So this is one insight that we have here. And the other limitation of prior works is shown here. On the left side, you can see the distribution of 500 random samples from cipher 10. And on the right, you can see the distribution of 500 vulnerable samples that are injected as canaries. It's very obvious that the privacy leakage, the difference between blue and the red dots, are more visible even under population of the distributions. Moreover, you might see why the average case MIs are struggling for privacy leakage evaluation. You can see it's very hard to fit a linear model that can effectively, with high precision and recall, distinguish the blue and red dots. So that's why we have approach like this. So, for example, here we decrease the observation points to few, and we only clearly see that if we want to measure per sample gaps, for example, for this number 13 sample, we can have more visible distinguishability. And this is what exactly we want to measure. We want to measure the difference between the green dot and the blue dot, that is the difference between unlearned and retrained distribution for efficacy evaluation. And we want to find the difference between the blue and red dots to find the privacy leakage. So let's summarize what we have till now. We said average case MIs are not strong because usually there are some output suppressions. And output suppression is not the same as a data removal, and we need to calibrate this impact. And we need a per sample evaluation, focusing specifically on vulnerable samples. So we only are interested in evaluating vulnerable samples for privacy leakage. This motivates us to propose our new framework named RULI. Our proposed framework is RULI, as we said, and here it's a framework to train shadow models and make the hypothesis test. In shadow models training, we train shadow models to estimate per sample distributions. We optimize this with splitting target samples into 3 splits. And here, by training n shadow models, we will ensure that we will at least have n divided by 3 shadow models for all the distributions that we require. And also in our framework, we introduce a simple calibration test model for efficacy. You might consider this test model as a router, that 50% of the queries that goes into this test model is coming from unlearned model, and the 50% are coming from the retrained model. But the adversary in game-theoretic perspective doesn't know from which model these are coming. So the test model is just behaving as a router that gives the queries to the adversary. And in this setting, because this test model is not existing in practice, we usually we call efficacy evaluations to be done by the trusted users and the model providers. And this will not break any fairness in the game-theoretic perspective. So we evaluated RULI on both vision and text datasets. Our focus was on 2 top-performing inexact unlearning methods: a scrub that maximize KL divergence under forgetting data, pushing prediction away from memorized information, and also a sparse fine-tuning. These 2 were performing best on previous benchmarks and evaluations. For Tiny ImageNet, this is an example of the results that we provide here for illustration. We fine-tune 3 small vision transformer, and the unlearning is only on less than 1% of the training data. RULI here reveals up to 69% MIS success, distinguishing unlearned with retrained samples on the right figure, highlighting a significant gap between the per sample evaluation of retrained and unlearned model, even if these 2 models are behaving very similarly on average accuracy. We also show how different targets matters in measuring privacy leakage. One exciting observation was that when we inject vulnerable samples as canaries to forget data, compared to the time that we forget data, when the forget data is only vulnerable samples, the privacy leakage is more significant. Here we tried injecting canaries as 50% of the forget data, but this trend exists for a lower percentage, like 5%. This highlights why we insist on canary injection for unlearning requests, not only to unlearning requests, not only for training pipeline. We also highlight the noticeable gap of RULI and the representative implementation of average case MIAs like population attacks that are using linear regression models to fit over a population of shadow models. We have a more comprehensive results on Cypher10. Interestingly, we observed the success of sparse fine-tuning on mitigating MIA attacks while maintaining low efficacy, achieving around 10% TPR at 1% FPR and up to 80% success rate. This shows that not all the time privacy leakage responds to efficacy. And we also extend our experiments on VKTeX for purpose of just generalization for language modeling. This time, our focus is to unlearn n-gram sequence when we have SFT and prefix mask training, and then unlearning using approaches like gradient ascent and negative preference optimization. Here is a real example of what is the unlearned data, not what is the unlearned sequence. That we just want to forget last 7-gram tokens of a text referring to the foundation data of the program. So what does this mean and what we want to achieve? We show that privacy auditing is distinct from unlearning auditing, and we should not conflict these two. Privacy auditing answers that this model leak information, while unlearning auditing is this model indistinguishable to retraining. And similar approaches of unlearning is applied to generative models. So similar problems might exist in another form there. The limitation is that RULI is very expensive because it requires lots of shadow models. And applying RULI to generative models and LLMs is not feasible because defining retrained models is very hard. And one mitigation is that we can estimate memorization we can mitigate the privacy leakage by estimating memorization and doing the sequential training that are in the paper. And thanks for the attention. You may contact us with the email, and our code is available on GitHub. And I would be happy to discuss collaborations or extensions.